They're an open cover of K. So, by compactness of K, there exists a what? Finite subcover. Let's give it a name. V sub. This is where you subscript the subscript. Ah, yes. Q what? 1 dot 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 V sub Q N. Little n. Oh, very nice. Help. Now what? So what should I do with the U's? Look at their partners. These are partner sets. So look at all the U's and take their. You could take the minimum radius. An easier way to say it is to take their. You've got a bunch of concentric balls. Take their intersection. That's probably an easier way. Then let's give that intersection a name. Let's call it W. If we take the intersection of the U sub Q1 intersect U sub Q2 dot 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 U sub Qn. What can I say about W? It's the intersection of how many things? Finitely many things. Therefore, it's an intersection of finitely many open sets. It is open. And if you really want to help the reader, you could say in its radius, it's a ball of radius, the minimum of distances between P and Q sub I. That's one observation you could make. Okay? That is another way to think about it. Okay, now what do I claim about W? So now I had all these partner sets here. And the smallest one is the one I'm interested in. That's a ball, but why does it miss the car? Because VQ is a cover. Okay, but why does this ball miss the car? Ah, yes. This creature is disjoint from, well, it's disjoint from, this circle is disjoint from its single partner. But what about, how do I know it's disjoint from all the things that cover this creature? Okay, triangle equality will be useful, but give me intuition. Why is it that this point, this disk, misses all the other, so here's another point. Let me just draw another point here. And its ball. Maybe I should do a different color here for these partner sets. So this is the partner that has this one as its partner. Why is this going to miss all the possible things, not just the one that corresponds to this one? Yeah, the green ball is in every set here. And every U, this green ball is in every U, but each U misses each V. Okay? So the green ball cannot be in the union of the UV. So that's this is the part where it takes a little bit of work. So the claim is W intersect each UV, each VQI is empty for each I. And why is that? Because, well, it's easy to see now the way I've written it, because W is in U sub Q, right? U sub Qi. And U sub Qi intersect V sub Qi is empty. Okay? Everybody happy? All right. So we are done. Why are we done? Because I found the desired Q. Okay, so maybe I should remind the reader. So W is the desired neighborhood. That's probably what I should insert here. W is the desired neighborhood. And the word desired makes the reader think, oh, yes, you referred to something that you wanted to show earlier. Okay. Any questions about this proof? So really what we have is, it's sort of an amazing kind of idea here that I can separate P from each point. There are infinitely many points, but that's where compactness comes in. Okay. Beautiful, beautiful idea. All right, so what do we know? If a set is compact, then it must be closed. So we have, as a easy consequence, something that you've already seen, and that is, for instance, example 0, 1, this open interval is not compact. We have already seen an open cover that doesn't have a finite subcover, concentric things getting bigger and bigger and bigger, right? But now we can see from this theorem that it's also clearly not compact. Okay, if it's going to be compact, then it has to be closed. Okay. Okay, very good. What else can we say about the relationship between compact sets and closed sets? Compact sets are closed, but are closed sets necessarily compact? No? Give me an example. How about the entire real line in the entire real line? It's not compact because it's not bounded. That's one way to see it, right? So notice that the entire R in R is not compact because it's not bounded, though it is closed. So closed sets are not necessarily compact. Or sets are not necessarily compact. Okay, Willie. If it's closed and not open, is it still compact? Well, excellent question. What about the set that goes 0? It's a ray starting at 0. Was that closed? Yeah, it's closed. And it's also not compact because it's not bounded. Excellent question. Yes, Emil? Ooh, excellent question. Are closed and bounded sets necessarily compact? We were going to answer that question next lecture, but since you asked, it'll turn out that closed and bounded sets are not necessarily compact it's not in every metric space, but it is true in R. Okay, and so that's something called the Heine-Borel theorem, which we will prove next time, and we're leading up to. Okay, excellent question. Harris? That was exactly the same question. Yes, that's a famous theorem where we're going to show closed and bounded sets are compact in R, but not necessarily in every metric space. Yes? For any set we pick, can we find a metric space in which it is compact? For any set? Can you find a metric space in which it is compact? Sure, yeah, you give me a set and put the for any, can you, right, so given the set that already has a metric, or you can pick the metric? Given a set? Okay. Well, yeah, so here's one thing you could do. You could ask yourself, what if I, yeah, that's a good question. And I should know the answer to this, but